do an unusual one today, a new substitution. Let's be our exam prep 3. So let's go back to our example with 5 and 4x squared. So we have 1 divided by square root of 5 plus, that's our trick, plus 4x squared dx. Because it's plus under the square root, there is none of those that you already know, that we can adjust this one to the known integral. So we have to do some substitution, but which one? In this case, when something looks like under the square root like a squared x squared plus b squared, that, then we can make a substitution, and the substitution will be that say ax is equal to b times tangents of theta. So where we're heading? We are heading to getting 1 plus tangents here square, and that will get second square, and then this root and that second square will be nulled. So let's see. In our case, what's our a? So say 2x is, so you have 2x here, so this looks like a squared x squared, so it's 2x on the power of 2. So we got 2x is equal to, and what's our b? But that also need to be a square, so it's square root of 5. So 2x is square root of 5 equals square root of 5 tangents theta. So the whole thing was, then you know that derivative of tangents is second squared, so that raises the power. So if we go dx becomes square root of 5 divided by 2 times what's the, so it's second, so the first differential of tangents is second square of theta. So if you now plug in that in our integral, it will look like 1 over from here we will have that is 4x squared equals 5 times tangent square of theta. So we can put that under the square root. We have 5 plus 5 tangents square of theta. And for dx, we got second square of theta d theta. So if you take this 5 out from under the root, I hope you understand this above. I wrote it quickly, so 1 plus tangent square is second square, so And this integral of second is from the previous examples. So you remember that's half ln of second of theta plus tangent of theta. Let's see. To do a back substitute, we can do that. We need second of theta and tangent of theta. Tangent of theta we can get from here. So from here we get that tangent of theta is equal to 2x divided by square root of 5, and you need second of theta. Just keep in mind that from here we can get second of theta because tangent of theta plus 1 equals second of theta. So second of theta is square root of 1 plus tangent square of theta. So if we apply that, so we have that 4 from here, 4x squared minus 5 equals tangent square of theta, which is equals the second square of theta is 1 plus tangent, so second square of theta, so tangent square of theta is second square of theta minus 1. Second square of theta minus 1. And then 4x squared minus 5 plus 1 becomes 4x squared minus 4 equals second square of theta, and second is equal square root of I just noticed an error. It's here divided by 5, it's multiplied by 5. Sorry for that. So we'll fix that up. So what we got, 4 divided by 5 equals tangent square of theta, and that second square of theta is then equals 1 plus tangent square of theta, so tangent square of theta equals second square of theta minus 1, second square of theta minus 1, so it's going to become 4x squared divided by 5 minus 1, and get rid of this, no, it's plus 1, sorry, plus 1, because it was minus on the other side. The common denominator is 5, but it's going to be a square root for there, so let's make more room here. So if we continue there, that's equals second square of theta and later from here. So what we got, the second is equal to square root of the common denominator is 5. So we have plus 5 for square root of theta plus 5. So it's 5 plus 4 square root x square root of 2. And that, if you divide it into 2, will be so like square root of there divided by square root of there divided by square root of 5. So that's what we have. So now we need to replace that into here. So we'll make some room and continue up here. So what we have 1/2 of, so what we're getting is 1/2 of ln of secant square is, the secant itself is square root of 5 plus 4x squared divided by square root of 5 plus tangents. We said the tangents was from here is 2x divided by square root of 5, and that's all plus c. And you can leave it as such, or we can take that common 5 out, square root of 5, and merge it with c if you wish. So we'll leave that as that for now. Let us continue with the differential equation. Let us continue with the differential equation. So say we have an differential equation like d of q by dt, they are usually dt 0.01 times p. So we have two variables, sorry, we'll put one variable, yeah, two variables, dt and, sorry, it was q here. So we have two variables here, variable t and variable q. So what did we say? Separation of variables. So we got dq by q equals 0.01 dt. And then how do you lose differential? By you apply an integral. So on both sides, respective to their variables, you apply integral. So what you're going to get there? You have 1 over q times dq. So of course it's ln of absolute value of q. And here you got this in front of the integral, and 1 is t, so you get just t. And our intention is to get just theta in relation to t. So how are you going to lose that? But what's contra function of ln? The opposite function is e on the power of something. So if I put e on the power of ln of theta, then that will null each other. So that nulls each other. And e on the power of that times t. So what I did, on something like that, yeah, something here, e on the power of that. So what you're getting that theta, or absolute value of theta, is equal to e on the power of t. What we forgot here is plus always plus c, but then you have e on the power of c. The power of c. So what you can do there, I can call that as, so you know that a on the power of b times a on the power of c equals a on the power of b plus c. So we have a plus here, right? So that means that from that there, that's the product, yeah? So there is product. If this is not clear, just to make this then more clear, so what we have on this side, we have 0.01 t plus c, and then all of it when you put e on that. So that's that bit, and that's that, and that there shows that bit there. Yeah. So therefore, our final is that this here times a constant, and we can then put it in front of here, say some a times that a replaces this inner c, e on the power of c. So that's our solution. So what did we have? Important is separation of variables. Separation of variables for that for differential equation. Now let's do an example with e of x. So example with e of x and integrals. And so to remember that e on ax, if you go first derivative, you get a on e at x. And if you have an integral of a on e on x, you'll get 1 over a times a, sorry, here is ax. So that's what we will use, right? So let's delete this and continue. So our integral, let's be integral of, say, 0 to 1 of e on the power of, say, simple x with the power of e and x plus 5 dx. So what we're gonna do there, so first, obviously when you have ex, the derivative of ex, so integrals talk substitution, right? Chain rule talk derivatives, so substitution. What you're gonna substitute here? E of x, it will become e of x, so that becomes derivative, can eliminate what the denominator with dx. So if you just simply say the whole lot, e of x plus 5 equals u, and I have du equals e at x dx. And that our integral becomes, so we don't need this, our integral becomes, so first when x is 0, then we have e on the power of 0 is 1, so u is equal to 6. When x is equal to 1, we have that u is equal to e on the power 1 is e. So we have that u is e on the power 1, that's e plus 5. So e plus 5. So integral becomes 6 to e plus 5 of ex dx is du, and here is u. So what we get is natural logarithm of absolute value of u, and that in the boundaries of from 6 to e plus 5. So that becomes ln of 6, ln of e plus 5, so it equals ln of absolute value of e plus 5, which is e plus 5, that's positive anyway, so it's just e plus 5, e plus 5 minus ln of 6, not 6 contra e and 6. And using the ln's, that means that the rules for ln minus and plus is ln of, sorry, it doesn't, we don't need the absolute sign anymore, we can keep it, we don't need it, e plus 5 divided by 6. And that's it. Let's do more examples with derivatives, and that's chain rule. So let's say p equals 4 pi a square. So, and we have, say, dp by dt equals 5, and say we wonder what would be dr by dt when r is equal to, say, 3. What would that be? So what we can see here, we want p in relation to t and r in relation to t, but we have here p in relation to r. So what we can do, we can write that dp in relation to t is the same as dp in relation to dr times dr in relation to dt. So that links our dr and dp in relation to dt. And this bit we can get from there as the chain rule. So what's dp by dr? That's differential of dp with dr is equal to 4 pi times 2 times r. So equals 8 pi r. So dp by dt, so dr by dt, so from there we get dr by dt equals dp by dt is 5 divided by dp by dr, which is 8 pi times r. And when for r equals 3, we have 8 pi times 3. So it becomes 5 over 24 pi. Let's do more differential equations. For example, you may have a case where you ask whether something is a solution to a differential equation. Say y on the second derivative minus, say, first derivative plus 1 equals 0. And say whether e in the power of, say, 2x is the solution. Is this a solution to the equation? Let's check. So e on the power 2x, first derivative becomes 2e in the power 2x, and the second derivative is the same as the first derivative of the previous one, which is 2 times 2 times e on 2x. So it becomes 4e on the power 2x. So if you put that back into the equation becomes 2 in the power 2x minus 4 in the power 2x plus 1 equals 0. That's obviously not. So that's obviously not a solution, because 2 in the power 2x equals 4 in the power of 2x minus 1. That's obviously not a solution. So it's not. The answer is e on 2x is not a solution to this equation. So that becomes 1 over 3 minus x times 3 plus x dx. So because we can't do integrals with the multiplication, we can split them into 2. So what do? We can rewrite this as a over 3 minus x plus b over 3 plus x. if you have a non-reducible bit here that is a quadratic form, then this one will be a quadratic as well. And up there you could have bx plus c. It won't hurt if you put bx plus c whenever you have a quadratic here, because if anything is to be 0, can come back to b, or 1, and c is 1, and so on. So what that becomes 3a plus ax plus 3b minus bx. That's that. Over the same. Oh, that's just the top bit, denominator. And now if we equal the denominator to the one above, so it should be 1 plus 0x. Yeah, there's no x. So therefore, with x we group, we have x is a minus b. Yep, so, and the x is 0, so we have that a minus b is equal to 0, and we have that 3a plus 3b equals to 1. From here we have that a equals b. If we substitute that in the second one, we'll have 3b and 3b, 6b equals 1, follows b equals 1/6, and a is 1/6 from the first one. So that makes our integral into 2, breaks our integral into 2. So the first one has a, which is 1/6, so we'll put 1/6 here, 1 there, and under we have the 3 minus x dx. And then for the second one we have 1/6, 1, 3 plus dx. So we can make a substitution, so we don't need this anymore. Substitution of 3 minus x to be our u, du equals minus dx. So that becomes 1/6 of integral over u, and the minus sign is here, times dx, plus the second substitution, similar, and the sign is no change because dx is positive. So here is du. du here. And du here. So what does that become? That's natural logarithm of u. So it's ln of u. For the first one, the absolute value of 3 minus x, and 1/6 is here with a minus in front. That's not nice. That equals minus 1/6, and plus this and the second one is 1/6 ln of 3 plus x and plus c. And knowing the logarithms, we have an absolute value of 3 plus x divided by 3 minus x. But before that, so this one, it goes under power. So let's do it again. We could have taken that 1x first. Up, so will be this first one will become ln of 3 minus x on the power of minus 1/6 ln of x on the power 1/6, and then becomes 3, and then becomes ln of 3 plus x and the power 1/6 x on the power minus 1/6 minus 1/6. And what that becomes ln of absolute value of, because minus 1/6 becomes plus 1/6 on the top, so what we got 3 square minus x squared, so it's 9 minus x squared, and that on the power of 1/6 plus the 6th root of that. So that's our solution. What we use here, we used non-identity that a and the third times b on the third equals a times b on the third. That's what was used to get that. Just to make one thing more backwards, this was used from here, this bit here, so that was equal 1 over, and brown into 2. So what we do, we did that before in maths previous years, so that is equal to that.